Hello, everyone. I'm Davis Wertheimer from IBM Research, presenting on behalf of myself and Supriyo, who unfortunately could not make it here today. This is Lessons Learned in WatsonX Training, Scaling Cloud-Native PyTorch FSDP to 20 billion parameters. As the title implies, we've spent roughly the last year and a half developing a platform for foundation model training, fine-tuning, and inference at scale, built directly on top of PyTorch. Now, Raghu and Priya gave excellent keynote talks earlier today on why we're doing this, the progress we've made, and where we are now. I'm not going to rehash much of that. I'm here to discuss how we got to 20 billion parameters and some of the interesting twists and turns we encountered in the process. And make no mistake, it is a process. You can't just build a platform for 20 billion parameter models directly. You have to walk before you can run. So it's more accurate to say that we actually built a training platform a while ago, or at least a first draft, and we've spent the last 18 months or so evolving it organically as we scale up to handle larger and larger models. Case in point, our initial try was just a small demo model with 110 million parameters, which only took a couple weeks to put together. The real effort was in scaling that model up to 20 billion parameters, because it's not so simple as just inflating the hyperparameters of your model and then letting the same code handle it. Scaling up the model size involves scaling up many things simultaneously, including the number of GPUs, for example. Our initial demo model used only 2, while recently we've employed up to 512 in parallel. The quantity of data. Our initial demo model used only a 200 megabyte Wikipedia dataset, whereas now we're training on over 10 terabytes of IBM web data. We've been scaling up the sequence length from 512 initially to 4K tokens more recently. We've also been broadening the families of supported transformer architectures, starting with simpler encoder-only models, broadening to generative encoder-decoders, and finally adding decoder-only for the full set of major transformer families. We've also had to expand our set of parallelization schemes, which I'll discuss later, to support these larger and larger models. And I could go on, but this graphic is already getting crowded, which brings me to my main point. Scaling up model pre-training is a long and complicated process. And so today, I'll be sharing some of the more interesting and unexpected lessons we've learned, as well as the work we've been doing with the PyTorch FSDP team along the way. I'll start by simplifying the problem a little bit. Most approaches to implementing model pre-training can be described as points in a three-dimensional design space. Every implementation has a footprint on each axis, and the vast majority of academic literature on scalable pre-training is devoted to minimizing any or all of these three footprints. The three axes are as follows. Computational effort. Training a model at scale involves applying a function with as many parameters as we can handle to as much data as we have available in as little time as possible. Solutions to doing so efficiently mostly revolve around parallelism. Indeed, the transformer architecture caught on in the first place because it was able to ingest long sequences efficiently in parallel. And of course, we can then further parallelize other aspects of training, such as model depth, model width, batch size, and so on. Lots of work happening in this space, plenty of which we've actually heard about earlier today. The second axis receives relatively less attention, and that's communication overhead. If you're training a model using only, say, 2 to 8 GPUs, then you really only need one physical computer, so communication between GPUs is very quick. However, scaling beyond that requires GPUs to talk to each other across different physical devices or different server racks. The efficiency of that process depends on the hardware and middleware of your multi-node cluster, which come in a wide range of price points and optimizations. Depending on your setup, your GPUs may spend more time talking to their sibling GPUs than on actual useful computational work, in which case your training dynamics will just look very different. And finally, GPU memory pressure. GPUs only contain so much space, and for large models, it can be difficult to physically fit the model onto the GPU, let alone leave enough room to actually do training with it. For reference, a mixed precision model with 30 billion parameters is the basic practical upper limit that we've observed for training on a single 80 gigabyte GPU. Beyond that, you need to start getting into some real design work. And speaking of design work, if we want to implement pre-training at scale, we need to establish some operating points or regions in this design space. To that end, we've been actively collaborating with PyTorch to implement, test, and scale a few different approaches, spanning this space and allowing us to handle different trade-offs between the different axes as required for different practical settings. The first approach is a mature and established baseline. We did not collaborate with PyTorch on this one, called DDP, or Distributed Data Parallel. For the sake of time, I won't go into much detail on these. I'm happy to discuss offline. But what you need to know about DDP is that it involves hosting a duplicate of your model on every single GPU, and then synchronizing each update so that your copies all move in lockstep. This makes DDP very memory hungry, and also relatively compute heavy, as we typically need to employ some extra tricks to make everything fit nicely on each GPU. The work we've been doing with PyTorch revolves around FSDP, or Fully-Sharded Data Parallel, which involves splitting the model over the set of available GPUs. FSDP is a beta feature of PyTorch under active development, and we've been working with the dev team to scale it up, test it, and iron out any issues. In FSDP, instead of duplicating the model, each GPU owns 1/nth of every layer, and those layer shards get passed around on demand as they're needed. As you can imagine, this reduces the memory footprint of the model substantially, but also increases the communication overhead by a factor of 3. I won't go into why 3 for the sake of time, but again, happy to discuss afterwards or offline. So DDP and FSDP represent two extremes on the communication versus memory and compute trade-off. So more recently, we've also been working with PyTorch on a hybrid scheme, where the model is split over GPUs within each physical machine, but duplicated across machines. This keeps the high FSDP levels of intra-node communication, but honestly that's fine, because intra-node communication is fast. Crucially, we're minimizing the slower inter-node communication. This is all while maintaining a relatively low memory footprint, 1/2 to 1/8 that of DDP, depending on how many GPUs you have per node. And of course, we're continuing to work with PyTorch on other approaches, tensor parallel in particular, but these initial 3 suffice to give us a range of flexibility to perform training of small to medium-sized models at scale, which in this case we'll say means up to 20 billion parameters. So we have our training configurations. Does that mean we're ready to train a 20 billion parameter model? And of course, if you have to ask, the answer is probably no. In this case, a resounding no. Just because you've configured your system to successfully take a single training step does not mean that you're prepared to do 250,000 in a row. It took a lot of work for us to get training with FSDP and HSDP stable over time. Here I'll share 3 illustrative examples. First, to run training with FSDP or HSDP, you need a very homogeneous workload. Both of these methods involve passing around weights for each layer one by one on demand, so you need very tight synchronization, not just across your different GPUs, but also between GPUs and CPUs, and between parallel processes within your GPUs and CPUs, such as the Python garbage collector and the PyTorch GPU memory allocator. Interrupting your tightly synchronized training loop with a different workload, for example, the standard validation loop that comes with just about every well-designed training script in existence, can cause unexpected behavior. This includes relatively harmless stuff like minor memory fragmentation, but also some real headaches, like not consistently reproducible and non-deterministic race conditions that freeze the entire job. Interestingly, we found that we are able to externalize or even outright remove most of these interruptions, including the standard validation loop. It turns out that validation loss closely tracks training loss for large language models just about always, as seen here for a 780 million parameter T5 model. This actually makes sense. Because we're training on such large quantities of data, it's common to not even finish a single epoch by the time we're done. This means that when we calculate training loss, it's usually on unseen data, or maybe data seen once, over 100,000 steps ago. And what is validation data but training data that the model hasn't seen? So in this case, train and validation loss are by definition almost the same up to sampling noise, which means that we can remove the redundant validation loss entirely to stabilize our runs. That said, some interruptions are still necessary. When you're training on 512 GPUs, 64 nodes, for days or weeks on end, hardware hiccups become not just understandable, but expected. We need to be able to recover from sudden failures without losing too much work, which means saving model checkpoints. Unfortunately, we found that saving checkpoints caused fluctuations in allocated GPU memory, the gap between the green and the red curves here. And more troubling, steady growth of the reserved memory over time, the orange curve. And that growth will cause out-of-memory errors if you let it go for long enough. Working with PyTorch, we were able to identify and expose the environment variable controlling the memory fragmentation causing this behavior. So with the right configuration, we can now keep resource allocation steady, even when interrupting our training loop for checkpoints. Our final stability anecdote involves prefix language modeling with encoder-decoder models. Prefix language modeling involves taking some initial fraction of a sequence, passing it through an encoder, and then using that output and the decoder to predict the rest of the sequence. This is an essential step of encoder-decoder fine-tuning. Now, you don't want your model to overfit to a particular prefix length, so we'd like to vary the prefix length batch by batch. Recall, though, that FSDP and HSDP require very tight synchronization, and changing the lengths of the encoder versus decoder inputs from step to step will very rapidly mess that up. We're talking about job hangs in the first 100 steps. Interrupting a steady training loop is one thing, but it turns out that having an unsteady training loop in the first place turns out to be much worse. We were able to work around this by combining two sequences with mirrored lengths in each line. Prefix 1 is the same length as suffix 2, and suffix 1 is the same length as prefix 2. This way, we can vary the prefix length batch to batch, or even line to line, but the input size won't change. And by using proper attention masks, we can recover standard PLM behavior, unlocking PLM fine-tuning at scale. So let's say we've now solved the issue of stability over time, and we have a range of implementations and approaches in our 3D design space for dealing with different hardware setups. Does that mean we're finally ready to train 20 billion parameter models? And again, the answer is a resounding no. There is a long tail, very long tail, of other rarely discussed practical challenges to wade through, and I'll briefly discuss some of the more interesting ones here. Recall what I said earlier about model checkpoints. We need to be able to recover from sudden unexpected failures. This means checkpointing relatively frequently. I glossed over it at the time, but this isn't a simple proposition, as these checkpoints are actually very large. A single training checkpoint for a small llama model is 81 gigabytes, which means you're saving these to cloud storage. And if you've ever tried to back up a large cache of family photos all at once, you'll know that streaming 81 gigabytes to cloud in serial can take a long time. In our case, over an hour. This means that saving one checkpoint every 12 hours results in an 8% slowdown of your training run, and it only gets worse from there. One checkpoint every 4 hours, and you're hitting a 25% slowdown. This is also assuming you can write that checkpoint in the first place. If you're running your job on a multi-tenant cluster, as we've been doing, there's usually some form of heartbeat or liveness check. Every half hour or so, every job needs to report that it's still alive and active. If you're stuck in the middle of streaming your checkpoint, you'll show up as a straggler, and your job will get evicted before it can finish. So clearly, a faster approach is needed. We worked with the PyTorch FSDP team to implement, scale, and test sharded checkpointing, where every worker writes 1/nth of the checkpoint in parallel. This reduced our large model checkpoint time from hours to minutes. We also provided assistance in enabling cloud-based storage. Checkpointing previously assumed file system write-through consistency, whereas Amazon Cloud Object Store, for example, provides only eventual consistency. So we helped coordinate the individual workers to prevent them from writing to files or locations that don't yet exist. Finally, I'll note that distributed checkpointing was a major release feature of PyTorch 2.1, but I don't want to spend too much time on this, as there was already an excellent talk on exactly this subject just an hour ago. On the topic of checkpointing, recall again that epochs for language data are very, very long, possibly longer than the course of training itself. If we're failing in recovering multiple times mid-epoch, then we need to recover not just the model and optimizer states, but the dataloader state as well. We therefore extended the PyTorch dataloaders to be stateful, so that when we load from checkpoint, we're guaranteed not to revisit data that we've already seen, unless it would be otherwise appropriate to do so. The dataloaders are distributed, allowing each worker to own fractions of datasets and fractions of dataset files. They are rescalable, so that we can scale up from 64 to 128 to 256 GPUs, and then perhaps back down to 128 if needed, while maintaining our guarantee of not revisiting scene data every time, even when the data ownership and partitioning scheme changes over the differing number of GPUs from run to run. We support reweighting of datasets, either through oversample rates, where an epoch is complete when each subdataset is seen exactly n times, or by defining exact percentages of tokens to come from each subdataset. And we build it to be modular, composable, and extensible. And honestly, this could be a whole separate talk. In fact, I actually just came here from a whole separate talk on data loading at scale, but for the sake of time, I'll leave it at that. Activation checkpointing. This is another technique for navigating the 3D design space. The idea behind activation checkpointing is that for particular layers, instead of storing the intermediate activations used to calculate the backward pass, we'll recompute them during the backward pass as needed. By discarding activations, we save substantial memory while increasing compute footprint due to the recalculation. Choosing which layers to store versus recompute leads to a range of different policies, all landing at different points on this compute memory trade-off. The figure provides some example benchmarks. Different policies can increase throughput on the y-axis at the cost of hitting out-of-memory errors sooner as we scale up the batch size on the x-axis. Interestingly, even though this is a pretty straightforward dial for trading compute versus memory, the choice of when to use it is actually dependent on your communication overhead. It turns out that if your communication overhead is much lower than your computational overhead, activation checkpointing is almost never a good idea. I don't have the time to get into precisely why it gets technical, but I bring this up because it's an illustration of how navigating the 3D design space, let alone all the other constraints that we've been discussing, can be very nonlinear and unintuitive. We've also had jobs crash due to CPU memory constraints. Note, CPU memory constraints, not GPU memory constraints. In a distributed data loader, each worker owns a data shard representing 1/nth of, in this case, a multi-terabyte data set. And if that shard doesn't fit in RAM, you need a custom streaming data loader. Our streaming loader pulls data on demand with minimal redundant file pulls. And without going into details, it took substantial extra design, time, and effort to ensure that our streaming data loader is efficient while still returning data in a properly uniform pseudo-random mixture. CPU latency. A network forward and backward pass involves many sequential, unfused GPU operations, and each one requires a CPU-GPU synchronization step to set up the appropriate kernel. Depending on your hardware, this can produce noticeable slowdowns. In one memorable case, we were able to achieve a 2x speedup of our forward pass simply by switching to a cluster with faster CPUs and no change in GPU hardware. We've all heard a lot today about Torch Compile, which removes these synchronization steps by fusing the GPU ops, and we're working with PyTorch to get this implemented at scale for FSDP, AutoGrad, tensor parallel, and so on simultaneously. And the list goes on and on and on. Every single one of these bullet points has killed at least one of our jobs at some point in the recent past. So to summarize, there's something of an 80-20 rule when it comes to training at scale. 80% of academic literature focuses on optimizing compute, memory, and communication overhead, but we actually only spend about 20% of our time on this optimization, and the other 80% on a very long tail of practical issues which don't really get discussed in published literature and which frankly aren't really publishable. So ultimately, if you want to do pre-training at scale, it's not just a question of how fast or well optimized your approach is. What you need is a robust, adaptable middleware layer with an open and communicative team behind it that can help you address these kinds of unexpected challenges as they arise. So I'll wrap up with a huge thank you to PyTorch, and in particular to the FSDP team for providing exactly that, and to you all for sticking with me through the end of a long day of presentations. So thank you, and I'd be happy to take any questions. Any questions? Oh, yes.
So are these learnings documented somewhere that we can use to replicate some of them?
So some of these have been written up in various PyTorch blog posts, IBM blog posts. Not all of it. We are planning to document a lot of this more fully. But yeah, as of right now, no. Just piecemeal. But yeah, it'll happen. Yeah, that was last session.
Is the data loader available? Have you released the data loader?
So right now, we're in the process of migrating sort of what we have in our closed source repo to our open source repo. The data loader is currently in the closed source repo. We have sort of a pared down, updated version in the open repo. And yeah, again, we're in the process of migrating. So some of it, not all of it.
Do you have the URL for the open repo?
Yes, it was way back at the beginning of the talk. Oh, yep, there we go.
Thank you.
Yep. So right now, I mean, I say we've scaled up to 20 billion parameters in the sense that we have run training jobs with 20 billion parameters. We didn't really get a real model out by the end of it. So for real training, we're still kind of on the scale of 7 to 13 billion. We do want to keep scaling that up. At some point, IBM was tossing around the number 100 billion. I don't know if that's changed. That's kind of a little bit above my pay grade. I mean, I know we're interested in hosting, Llama 7DB at some point, so that's certainly at least that large. All right.
Thanks.
Thank you.